Good morning, everyone. Good morning. So I'm the first one to speak today for my lecture. So my name is Dr. Benny Ng. I'm the one that kind of created this program for you guys. So first of all, welcome to come to University of Hong Kong. This is the second time we are organizing this program. So hopefully you guys will have fun today. Okay. So this is my talk. It's blank. And people said an image is like 1,000 words. So I'm going to start my talk by showing you a series of images first. I think I've already spoken for more than 7,000 words, and I feel like that's maybe the end, should be the end of my presentation. But at the same time, I put on you an explanation of the hidden order in nature. So this is what we're going to start. The hidden order in nature. Okay, so you see all these 7 images, and I'm trying to explain to you the hidden order behind all these images. Can anyone tell me what's the hidden relationship among these numbers below? Yes, please.
When you add two consecutive numbers in this sequence, you get the next number.
Okay, are you sure?
Let's say you pick 5 and 8.
Okay.
When you add 5 and 8 together, you get 13, which is the next number. You get the 13, which is the next number in the sequence.
Mm-hmm. Do you guys agree? Yes or no? Okay, good. You guys are pretty sharp today. Okay, so yes, we have our gift person, and you deserve a well-deserved prize. Okay. So that's correct. Basically, you look at the sequence, 1 plus 1 equal to 2, 1 plus 2 equal to 3, and so on. You keep adding the 2 numbers together, you get to the next. Okay, and this particular sequence discovered by a mathematician, okay, Fibonacci, and that's why we call this a Fibonacci numbers. Okay, now, I showed you all the images at the beginning. We talk about Fibonacci numbers, then how do these plans have to do with the Fibonacci numbers? Okay, please.
Showing the golden ratio and 1.618, and so the patterns in it.
Okay. Is that right? Do you guys understand what he's talking about? The golden ratio. Well, people sort of fascinated by this kind of Fibonacci number, the sequence, and also patterns in nature. Okay, so they try to do their very best to try to look for this stuff. Okay, let's see if this is actually true. Okay.
Let's check out the bottom, 8 and 13. If you wanted to draw a mathematically realistic pinecone, you might start by drawing 5 spirals one way and 8 going the other. I'm going to mark out starting and ending points for my spirals first as a guide, and then draw the arms, 8 one way and 5 the other. Now I can fill in the little pinecone things. So there's Fibonacci numbers in pinecones, but are there Fibonacci numbers in other things that start with pine? Let's count the spirals on this thing. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The leaves are hard to keep track of, but they're in spirals too, of Fibonacci numbers. What if we looked at these really tight spirals going almost straight up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. A Fibonacci number. Can we find a third spiral on this pinecone? Sure, go down like this, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But that's only a couple examples. How about this thing I found on the side of the road? I don't know what it is. It probably starts with pine though. 5 and 8. Let's see how far the conspiracy goes. What else has spirals in it? This artichoke is 5 and 8. So does this artichoke-looking flower thing, and this cactus fruit does too. Here's an orange cauliflower with 5 and 8, and a green one with 5 and 8. 5 and 8. Oh, it's actually 5 and 8. Maybe plants just like these numbers, though. Doesn't mean it has anything to do with Fibonacci, does it? So let's go for some higher numbers. We're going to need some flowers. I think this is a flower. It's got 13 and 21. These daisies are hard to count. They have 21 and 34. Now let's bring in the big guns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 20, 24, 42, 53, 54, 55. I promise this is a random flower and I didn't pick it out especially to trick you into thinking there's Fibonacci numbers and things, but you should really count for yourself next time you see something special.
Okay, so actually, if you don't catch what she said, basically the pinecone image I showed you, you can actually find 2 of the Fibonacci numbers. Okay, in this case, 8 and 13. For the sunflowers, for example, you can have 21 and 34. Maybe this is something that you never figured out before. Maybe you saw, oh, it has some interesting pattern. But next time you go to a flowery shop, pick out a daisy or sunflower, start counting. Okay, maybe you'll find something interesting. Now, Fibonacci's numbers have many different properties. Okay, one of the properties that's related to coming out from the Fibonacci numbers would be the golden ratio. Okay, as the student just mentioned earlier. Okay, so how do we calculate the golden ratio? The golden ratio basically by dividing by 2 consecutive Fibonacci numbers. Okay, so for example, 1 divided by 1, you get 1. Okay, but then now you know the next Fibonacci numbers are 3 and 2. So 3 divided by 2 will be 1.5, and you keep doing this. That numbers will eventually converge to 1.61804, okay, approximately. Okay, so this is what we call the golden ratio. Okay, next pictures. I have lots of pictures for you guys. So now, can you guys tell me where is the golden ratio in here? Where's the golden ratio? Snow White, Beauty and the Beast, Sleeping Beauty. Can you guys find it? Let me tell you where it is. Right there. The golden ratio, 5. It's right here. Okay. Now, once you know the golden ratio, okay, once again it's 1.618. Okay, so you can define something called the golden rectangle. The golden rectangle, you can think of it as, okay, you have the length of 1, okay, then the other length will be 1.61804, okay, so that will be defined as the golden ratio. Okay, so what can we do with the golden ratio? Basically, how can we draw it? Basically, you can start from a bunch of square, okay, with the length of a Fibonacci number. So for example, you can start with 1 and 1, then the next number will be 2, and then you keep drawing a bunch of square. Then for every square you combine, basically you're making a rectangle. Okay, so all this rectangle that you're seeing right here, they're all golden rectangle. Okay. Now, after you have the golden rectangle, you can make use of that to make your golden spiral. Okay, as the student mentioned earlier. Okay, basically looking for the 2 diagonal angle and then just draw a curved line. But in general, nature actually follows more a general trend. Okay, there's something called the general logarithmic spiral. Okay, it's more general than the golden spiral. For example, from the ocean, you can see from the Nautilus shell, from the sky, okay, low pressure area over Iceland, okay, a hurricane, you see those, so over the sky. Not only that, even the spiral galaxy. So not only just from the ocean, from the sky, but also from the universe. Okay, you will see this kind of spiral pattern. Now, because of all these interesting properties that we've seen, people have been kind of inspired by this nature or the hidden message and try to build or imitate the nature. Okay, for example, architect building, the Eden project in UK, British National Wildfire Center. And people also try to use it for product design, for example. Okay, we have a Fibonacci lampshade. Okay, so you can go back home and start counting what is the Fibonacci numbers on those. Or also even a Fibonacci cabinet. Okay. Now, I'm going to switch topic a little bit. Now we're going to talk about something called the fractals. Okay, fractals are a very difficult concept, but the only thing I would like you to know is that if you want to know something whether it's a fractals or not, look for cell similarity. Okay, basically what does that mean? By zooming in the image, you basically see the same pattern over and over and over again. Okay, let me show you a video, and hopefully you will understand what I mean. I'm looking at a furnace, I'm zooming in a furnace, and then afterward, you get closer, you basically get the same pattern over and over and over again. Okay, when you see this situation happen, that particular object will have a fractals image. Okay, now I've been showing you guys a lot of plants. Okay, but it's not just plants. Okay, let me go to the next one. Other example. I don't know if you guys seen this before. The Russian nesting doll. Okay, it's a cell similarity. Okay, from the big one you open it, you get a smaller one. You keep opening, you get a smaller and smaller one. But it's a cell similarity. Okay, people also inspired by that and create products like that. Coastal line. Okay, that's another one that you can see fractals. Now the next part basically is called the tessellation because it's related to one of the workshop that we have today, the MOSAT workshop. Okay, basically it's a tiling of a plane to fill a plane with one or more geometric shape without any overlaps or gap. Okay, so typical example, honeycomb structure. Okay, for this you see all the regular hexagonal shape. Okay, repeated, no overlap, no gaps. And what we have today for the workshop 3, the MOSAT workshop, this is what they're going to build today. Okay, I'm just giving you this preview of what you guys are going to do today. And all the fish here in this particular image, they're actually all at the same size. Okay, it may not look like that way, but they actually are. Okay, but you have to understand a little bit called the non-Euclidean geometry. But at this level, it's not really an easy concept to explain, but I just want you to know at least the key message for this particular painting we choose is that for the non-Euclidean geometry, under the non-Euclidean geometry, all the fish here, they're all the same size, even though it may not look like that way. Okay. And that's conclude my talk for today. So you saw all these images, and all of them have a little bit of the hidden order in nature, and hopefully next time from now on, when you start observing nature, you see some more hidden order in nature. Thank you.